So I do a split where I take some example and I partition this example in 2 sets here and another set here. And then I can split again this partition into the training set and the validation set. We are doing it in 2 steps because I will show you a method where if you don't have a lot of data, you can do a trick to still be sure that the model is not cheating. So the first thing is cross-validation. So in cross-validation, I will have 1 experiment per model, per hyperparameters, and I will train the model on the train. I will evaluate it on the valid, and I will have 1 performance per experiment. And I will take experiment B because the performance are the best here, and I will test. If you don't have a lot of data, what you can do with this partition training validation set is to do a rotation of the validation set. So we will call it splits. So the first split is the first elements in the training set, the last elements in the validation set. Here I will use the middles, the examples in the middle for the validation set and the 2 others for the training set. And you can see that at the beginning, I will fit the hyperparameters in the model for each experiment once and for all. And then I do my training for each split on the associated training set. And I evaluate on the validation set. So I will have this table. And now I can do some statistics over the rows of this table. So here I will have an average of the performance associated to experiment A, average performance for B and for C. And I can also compute the standard deviation, the empirical standard deviation. So if there's some noise that the performance metric vary because of the choice of the validation set, I will be able to measure it. But it's really when you don't have a lot of data where you can feel that I don't have enough data in my validation set and where k-fold cross-validation becomes interesting. When you are using benchmark data set in deep learning with like 100,000 examples or millions of examples, you can just use cross-validation like this. And again, when I choose the best experience, I must do a final check on the test set. And if the performance of my test set is inside the range, the uncertainty defined by the standard error around the average, then I can be confident that everything is good for generalization, and I can be more confident to deploy the model. Okay, so now the job of data scientist is done. We have the best model. We want to deploy it, and we will do some engineering, because now we are scaling this model to maybe millions of users, or maybe we will deploy this model on a cell phone. So the first thing to think is, how can I detect and deal with prediction errors? Because it's not true that you will have 100% accuracy on your test set, and you will never have any errors in production. Errors are part of real life. And how can I detect these errors before providing the information to my user and dealing with this error? Maybe I can use another model which is less good, but at least for this given data point as an input, maybe it can provide me an alternative prediction which is not an error. Also, I can use default values if it's possible. The other point is that maybe in engineering you will have other constraints that must be respected, like the latency, the time between when I do a request and I receive the answer, the memory usage of the model, or the computational power that it uses. And these concerns are super important, but they should not be taken into account at the first iteration of the work of the data scientist. The data scientist should be free to explore, to use any possible models. And when we have a good model, it's much easier to simplify this model to take into account these constraints than really from the start restricting the different model that I can use in my experimental protocol. We can respect this constraint maybe in a second iteration of the experimental protocol. The last point is, how to really evaluate the impact of having a better model in production. Maybe the model is just one little feature in my overall system, and even if I have a very good performance metric, maybe my user will not even see the difference. And it's important too to measure this. And if the system is very complicated, A/B testing is maybe the only way to measure it. So I will deploy one system with my old model, one system with my new. I compare if it has an impact on my user, and if it has an impact, and I can see that I have a big gap in my performance metric, it means that the performance metric is correlated to how my user perceives it. You must do it several times to be sure that the correlation exists, but it means that you have a good metric. If the metric is better for the new model and you see no difference, then maybe reconsider using another performance metric for the next iteration.